Alrighty, everyone. This is a quick tutorial, hopefully, on something called molar volume. Molar volume typically is just defined as any ideal gas at STP, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere, takes up 22.4 liters of space, of volume. I want to use this term a little more loosely so that we have something synonymous with molar mass. Molar mass was some number of grams per mole of a substance. That allowed us to have a nice conversion factor of grams over moles or moles over grams. I want to be able to do the same thing, but instead, I want not grams, I want volume. Volume, volume is liters. Liters per mole. That way we can do liters over moles or moles over liters and get a nice conversion from moles that we can get from a balanced chemical equation to liters of a gas that is produced instead of grams. So how are we going to get there? Well, we need the ideal gas law. PV equals nRT, pressure, volume, number of moles, rate constant, and temperature. I'm assuming you've watched the other few videos on this, so these are not new to you. But real quick, pressure is in atmosphere for this, volume is in liters, N is moles, the rate constant for the ones we'll be using will be this rate constant, 0.0821 liters per atmosphere, or liters times atmosphere per Kelvin times mole. That's weird, but all those cancel out nicely. Again, if you watch one of the other videos, you can see how they cancel. And temperature is often given in Celsius, but needs to be converted to Kelvin with a plus 273. If you algebraically rearrange this formula, that will allow us to solve for molar volume. V, volume, equals nRT over P. And all we have to do is assume 1 mole. Just like molar mass assumed 1 mole to get a conversion factor, we're going to do the same here. Assume 1 mole. Then we want to solve for, all right, how much volume does that 1 mole take up? And then we need our givens. We have 20 degrees Celsius. This is approximately room temperature. And 1 atmosphere, sea level. So plug those in. We've got 20 degrees Celsius plus 273 is 293. And atmosphere's pressure, 1. Now all we have to do is plug and chug. V equals N was 1 times R, 0.0821 times temperature. So temperature, I would even circle that to make sure you don't accidentally do the wrong one, 293 divided by pressure, and pressure was 1 atmosphere. Plug and chug this through. The 1 times doesn't matter. You can drop the 1. Dividing by 1 doesn't matter. That doesn't change the number. Your solution to this is 24.0553. We have 3 significant figures here, so I'm going to round this to 24.1. Don't worry if you don't really quite understand significant figures. Just don't give me like 10 decimal places. Keep them near the neighborhood of the other numbers. And this is units or liters. Volume is in liters. So 24.01. Make sure this makes logical sense. The traditional molar volume, the standard one, is 22.4 liters at standard temperature and pressure. This is very close to it. It appears as though we did our math correctly. Atmospheres is the same as STP, and the temperature is slightly higher, 20 degrees Celsius higher, and gases take up more space when they're warmer. You probably know this intuitively if you have left a screw-on cap soda bottle out in the sun, and you come back half an hour later on a hot day, and it's like poof, it's expanded, and when you take off that lid, it really poof. All right, if you feel good, video's done. All right, if you're like, I could use with a little more practice, then go ahead and try this problem and then check my answer key. If you're like, Kyle, please just explain it one more time to me, then just stay with me and we'll do that. I'm going to pause for 5 seconds here for anyone that wanted to pause and solve this problem using a different set of givens. 30 degrees Celsius, 1.2 atmosphere. 5, 4, 3, 2, 1. All right, again, what we want is how many liters per mole. So to do that, we assume 1 mole, and we want to know how many liters will that 1 mole occupy at whatever the pressure and temperature are given in the problem. In this case, 30 degrees Celsius plus 273 brings us to 303 Kelvin. I'm going to circle that to make sure I don't accidentally use 30. And atmospheres, 1.2 atmospheres. Now, plug them on in. Remember, you're using the ideal gas law rearranged, so you're solving for volume. And then, just put them on in. 1 mole times the rate constant, 0.0821, times, multiplied by temperature in Kelvin, 303, divided by atmospheres, 1.2. Right. There we go. Now quick math there. We have 0.0821 times 303 divided by 1.2. Making sure my calculator has the numbers I just read and wrote, and those look good. So we are going to have 20.7303. If I round that to 1 decimal, that's liters, 20.7 liters. And that's that. Good luck.